So I was already introduced yesterday, but it's nice to be introduced again. And so since it's already my time to speak, I'll just introduce myself. Just joking. So we didn't get through the entire presentation yesterday, so I'll take off where I left off. And before I take off, I'll just run through all the slides to capture in short sentences what we saw as a means of recapping. Um, and you are on, so why doesn't this work? Yes, fantastic. All right, we had a motivation. And there are various definitions of SNARKs, and the idea is that we split up the computation in the prover and the verifier, and the way we build SNARKs is by giving the verifier superpowers, which we then strip away through cryptographic simulation. And we see a couple of superpowers. Interaction is one of them. Point queries in long vectors is another one. Low-degree tests is another one. Evaluation queries to a polynomial is another superpower. And we've already stripped away this one. That was the IOP model. And by the way, there's this whole compilation pipeline that follows from stripping away superpowers from the verifier. All right, so we study arithmetization where you need to define a state space, a transition function, a set of constraints, and so on. And we have the arithmetic execution trace, which is a table of values. Going down means going forward in time. And there is a bunch of multivariate polynomials that have to evaluate to 0 to indicate that they are satisfied. Then we're using divisibility as the fundamental tool to make succinctness real. And verifiers have to be nice and structured. So the idea of deep Ali is interpolate, compose with the air, then divide out the verifiers. And we can pass over this real quick. The domain is a subgroup of order to the k of the field, which you can identify with equally spaced points on the circle. This gives rise to a sparse verifier x to the n-1, which you can evaluate fast, even though the degree is reasonably large. Okay. It's deep. We want to reduce this polynomial IOP to a low-degree IOP, and to that effect, we identify polynomials with their code words obtained by evaluating those polynomials on another domain D, and that other domain D also consists of equally spaced points on the unit circle, just a lot more. And since we're doing interpolation and then evaluation, we're actually just going to merge those two steps into low-degree extension. Then we have the deep update, which is a single point, point-wise map that we can apply to a vector to obtain a new vector. That's very powerful. But in the end, we only have a noisy low-degree test, which means that we have to reject considering vectors that are sort of close to the code. Either the vectors are far from the code or they are in the code. And that means that we always have to consider this distance parameter delta, which is very important. Okay, deep soundness. Based on how big this delta is, you get a huge list or a small list, which makes this soundness probability negligible or not. Here we have the list decoding conjecture. And that was the reduction of a polynomial IOP to a low-degree IOP, which is made complete here. Now we can continue with adding in a low degree test, which is the superpower that we previously had, and now we're going to strip away a low degree testing superpower simply by adding in a low degree test. So that is the arrow in the middle of this diagram. And actually, it's instructive to have a little bit of a digression here. So let's look at batching. If you have a look at the protocol here, there are a whole bunch of vectors that you need to test the low degree-ness of. So X, bold X, all the way at the bottom here. Bold X is itself a matrix whose columns are vectors. And we actually want to test several of such matrices. I iterate over them and call them X one by one. And every one of those columns in every one of those matrices has to be tested for low degree-ness. That's part of this protocol. And the idea behind batching is, why do we have to do so many low degree tests? Why can't we just get away with doing one? And the answer is yes, we can. We can batch them. And if you start thinking about it, the first solution that might come to mind is to just assign a random value, random scalar to every vector, and then take a random linear sum. Does that sound? Pretty much yes, but there's a little more context to it. So you have to consider the probability. This is simplified towards two vectors, matching two vectors, but it generalizes to an arbitrary number of vectors. You have to consider the probability that we're starting from two vectors, u and v, of which at least one is far from the code. And then we sample a random point on the line connecting those two vectors. And the question is, what's the probability that that random point is close to the code? And this gives rise to the proximity gap, for which there is also a conjecture. So once again, we need to consider the Reed-Solomon code. And once again, we are considering various radii, timing distance-wise. And so we need to consider a straight line connecting two points, u and v. And we're interested in the proportion of points on this line that are close to the code. So in the diagram within one of these balls. Now, if that proportion cannot lie in a certain interval contained between 0 and 1, so let's say epsilon 0, epsilon 1, where the smallest is still larger than 0 and the largest is still smaller than 1, if there is such an illegal interval, then the code exhibits a proximity gap, and then the code can be used for batching. So codes that do not exhibit such a proximity gap, unfortunately, you can't batch them. But fortunately, Reed-Solomon codes do have proximity gaps. And they have proximity gaps for some radiuses, some radii, not for all of them. All right, so this picture once again captures the gaps in our understanding of Reed-Solomon coding theory. This is a graph for growing delta going from left to right. And it captures known proximity gaps. And this graph is actually the same graph, or very similar to the one I showed previously about list coding. It's not an accident, but it is definitely a different conjecture, and definitely a different theorem also. So right up until the Johnson bound 1 minus square root of rho, where rho is the rate of the code, we have provable proximity gaps. and even epsilon there is quite usable. Beyond the covering radius, that's 1 minus rho. The covering radius is precisely the radius delta for which any point in the ambient space lies in some Hamming ball. That's what defines the covering radius. So at that point, there is no epsilon zero anymore because all points of every line lie close to the code. So it doesn't make any sense to think in terms of proximity gaps after the covering radius. But there is obviously a gap in our knowledge. We don't know what happens between the Johnson bound and the covering radius. And the conjecture states that we still have proximity gaps here. So if people say they use conjectural security for their Starks, that means that delta lies somewhere in this region. All right. So we have a delta and an epsilon. And we can use that epsilon to capture the probability that a random point on the line connecting 2 points lies close to the code when at least one point on that line is known to lie far. So we can use this proximity gap and take out the epsilon zero, and that's exactly the expression that captures soundness of batching. Proximity gaps and batching, they're two peas in a pod. Fantastic, we can batch. Okay, excellent. So we've managed to reduce the complexity of many low degree tests to just the complexity of one low degree test. Right. That intermezzo was no accident, and the timing wasn't either, because what follows is a very widely used proximity test called Frye. And I'm going to explain how Frye works in terms of batching. And I'm going to derive a soundness expression for Frye from the soundness expression for batching. Right. So once again, we have a step in which we strip away a superpower from the verifier, but this is a very incremental step. So on the left, the verifier can do low degree tests of length n over rho. Well, low degree tests on vectors of length n, testing for degree n over rho. And on the right, the verifier has low degree tests for vectors of length n over 2, testing for degree n over 2 rho. So the vectors have halved in length, and their rate is still the same across these two worlds. And we want to use the verifier on the right to simulate the verifier on the left. So basically, at some point, the verifier on the left receives a vector P from the prover and wants to test whether that vector corresponds to a code word or is far from the code. The code being the code of length n. What the verifier on the right is going to do is he's going to split this vector in two vectors of half the length, the same rate. And then he's going to batch them, and then he's going to test the batched vector using the low degree test of half the length. All right, so the question is, what does this split function look like? Turns out fast Fourier theory gives us a very nice and elegant split operation. Remember, we're taking a vector of length n and we're turning it into vectors, excuse me, n is not the length of the vector, n over rho is the length of the vector, n is the length of the trace domain, n over rho is the length of the evaluation domain. Anyhow, we're taking vectors of length n over rho and producing two vectors of length n over 2 rho of the same rate. If the original vector was a code word. And Fourier theory tells us it's a good idea to look at the vectors of even coefficients and vector of odd coefficients. And there are, in fact, straightforward algebraic ways to compute those. And we can even apply this decomposition using pointwise maps on the code word. And here we go. This is a pointwise map. You just take two elements of your vector spaced apart by half the vector's length. On the one side, you add them. On the other side, you subtract them. And in both cases, you divide by 2. In the second case, you also divide by x, or the value of x in that domain point. So polynomial expression and the code word expression is basically the same thing. So I showed you a trick. Your first reaction should be, how sound is it? Okay, this is actually a trick question in this particular case, because we're interested in the probability that either the vector of even coefficients or the vector of odd coefficients, I'm talking about their code words, is close to the code, given that the original vector is far from the code. And if you inspect this probability expression closely, you will wonder, where's the probability variable? And the answer is there isn't any. So it's not really a probability expression, it's just a proposition. It's true or it's false. So we can investigate, is it true or is it false? Well, it turns out that the map that sends f to its two components is linear and invertible, and therefore it sends pairs of 0 elements to 0 columns and non-zero pairs to non-zero columns. So it preserves errors, and therefore it preserves distance, and therefore the proposition is true. Soundness error is 0 for the split operation. And so, armed with this split operation, surely we can just split a logarithmic number of times and then have very short vectors and then just test those for low degreeness, right? What's the problem with splitting a very long vector into two a logarithmic number of times? You end up with an exponential number of vectors. So, what do we do? Well, prover helps. And in order to verify that the prover is not being malicious, the verifier needs to verify prover's help. And so, in particular, the help that the prover is going to give the verifier is batching. So this is the bones of the protocol. Split, batch, split, batch, split, batch. That's right. Okay. This is the same protocol in a little more formal terms. The verifier and prover both have a vector A. The verifier samples a scalar. The prover splits this vector into even and odd parts and uses that scalar to batch, sends over the batched vector. The verifier samples a new scalar and sends it to the prover. Prover splits and batches and sends over the batched code word. And this happens however many times it needs to happen for the verifier to end up with a very short code word, which you can test for low degreenness trivially. That was the commit phase, right? This is where the prover helps by batching. But there's still a check left to be done. The verifier doesn't trust that the prover helped correctly. He needs to verify this. And so the verifier is going to open up all the code words in a bunch of indices sampled at random, such that he can check the local pointwise map in those indices. the verifier samples enough indices, then you can bound the probability of cheating provers getting away with cheating. So I showed you a protocol. Your first reaction is? Foundness, exactly. So we have to be concerned about two different things. Suppose that this protocol consists of R rounds. We have to be concerned of two different things. One is one of the scalars just so happens to have been unlucky and sends one or two far code words to a close code word. Yeah. Unlucky scalars. It happens. We can bound this using the proximity gaps epsilon 0. Great. And then the second event that we have to be concerned about is the indices sampled by the verifier at the end of the protocol fail to expose false pointwise maps or inconsistencies in this pointwise map. So what do I mean by that, bad indices? Here's a visual representation of the Frye protocol where we look at the code words that are being sent. In every round, the code word that's being sent has half the length because the prover folds them, splits them, and batches them. And split and batch you can think of as folding. And then the very last code word is obviously opened by the verifier who tests it for low agreement. That's the commit phase. And in the query phase, the verifier samples one index. This index percolates across every code word modulo that code word length. And the verifier opens the code words in that point and verifies that it was correctly computed from the previous code word opened in the same point and its counterpart shifting by the half of the code word length. So as a practical matter, you don't you make sure to reuse computational results. Was that a question?
Yes. So when you say he samples indices, the verifier, I guess, he samples say characters from the word that is the code.
No. These indices live between 0 and n over rho.
All right, but do they represent positions?
They represent positions in the code, in the code word. Yes.
Right. So I'm guessing that then the verifier performs the batching operation on those indices.
The verifier does not perform the batching operation. The prover performs the batching operation. The verifier opens the code words in these indices, so reads the code words in these indices in order to verify that the batching was done correctly there.
Okay. Right. Thank you. And how much are we very much concerned of the number of indices allowed?
Very much concerned.
Okay.
Very much concerned. I should let you finish my slides because your question is provoking exactly the next animation here. So let's compare the false code word, false vector that the prover starts with to some code word. When you make that comparison, you will have to identify a whole bunch of positions in that vector that are erroneous. And we know, since we are considering vectors that are delta far from the code, that these regions of errors must span a proportion larger than delta. Okay, and we also know that after that many folding steps, the verifier checks the code word, checks the short code word for low agreements. And so, if any one of the any one of the blue indices points into one of the regions of errors, that error will percolate down and the verifier will observe it in the final code word. So the question of the indices revolves around how many indices do we have to sample so that we are guaranteed to find one of the errors with high probability. And once you do that calculation, you'll see what's the probability that one index points to an error that's greater than delta. The probability that one index points to a non-error is less than 1 minus delta. The probability that t indices all point to non-errors is 1 minus delta raised to the power t, because these indices are obviously independent. T, the number of indices, is a big factor affecting proof size. Down the line, we will put all of these code words into Merkle trees, and for every Merkle tree, the verifier will have to open T leaves of the Merkle tree. All right, so this is where we add the low degree test, try, onto the running protocol, deep LE with the deep trick applied. And so this is just concatenation, really, of protocols. After we get to the point where we have code words that we need to test for low degreeness, or vectors that we need to test for low degreeness, we batch them and we apply fry. And fry itself is split then batch, and so on. So soundness, we inherit all the terms that we have accumulated up until now, and we need to capture the soundness of the extra bits of the protocol, which I already captured on previous slides, right? That's R times the epsilon from the soundness gap, which itself depends on delta zero, and 1 minus delta zero to the power t, where t is the number of indices. The middle term captures the probability of bad folding in the course of fry. The bottom term captures the probability of sampling unfortunate indices. And I guess I forgot the green term on top. That's the probability of bad batching, where you combine a large number of vectors. Okay, that was low degree testing. At this point, we have a proper IOP, because the only superpower that the verifier has is to look at individual locations of vectors that were sent to him by the prover. Why is that a superpower? Well, it's because the prover still needs to commit to those vectors and cannot lie about the values of those vectors in points that the verifier doesn't open. And the BCS transform captures why this is a superpower. You can look at the BCS transform as answering that question through a construction, turning it into a concrete interactive proof. And so we're going to transform a IOP where the prover sends vectors to the verifier, and the verifier can read those vectors and select points, but ignores most of it, into an IP where the verifier does not get to ignore messages anymore. And this is the way we do it. If you're familiar with Merkle trees, we just Merkleize every vector. And then whenever the verifier wants to read one of the vectors in a given index, he sends the index over to the prover, and the prover opens the Merkle tree in that index. That's it. That turns out to be sound. I'll get to a concrete expression for soundness later. For now, for those people who are not familiar with Merkle trees, this slide is for you. If you are familiar, you can sleep for a short 2 seconds. A Merkle tree is a balanced binary tree where at the bottom we have leaves, at the top we have the root, and every pair of nodes in every layer is hashed together to produce their parent. we can open a leaf by supplying all the siblings of nodes on the direct path from the leaf to the root. Why is that true? Because with the leaf and all the siblings, the verifier can walk up back to the root and verify that the rederived root is the original root that was committed to. So this gives rise to a commitment scheme. The prover sends the root, the verifier samples an index. The prover provides the leaf at that index and the authentication path, which consists of the siblings of all nodes on the path from that leaf to the root. And the verifier then walks up. Okay. Soundness. How sound is this? We're interested in the probability that the verifier accepts a leaf as though it was committed to it, that is, it accepts the statement, the ith leaf of this tree, whose root is x, equals y. That's accepting, even though the original leaf was different. Well, if the prover manages to convince the verifier of this fact, even though it is false, then the prover needs to know a collision, which means that the soundness error is bounded by the probability of finding collisions. Now, if we're going to use a concrete hash function, then there's a concrete insecurity function there that we don't really know. And I like simple security proofs, even if they are slightly unrealistic. So let's work in the random oracle model, which means that the hash function that we use really is a perfectly random function. You know nothing about the distribution of its outputs until you sample them by evaluating the hash function. And then it gives you something that's uniformly randomly distributed. All right, if we work in that model, then the probability of finding a collision is bounded by the number of evaluations of the hash function through this expression, right? Q is the number of times that the malicious prover evaluated the hash function, and he's going to collect all the outputs of this evaluation, and he's going to check for collisions. And so what's the probability that there is a collision in his list of outputs? Well, that's Q times Q minus 1 over the size of the output set. And so you want to have a output set should be twice your security level, because Q is in the numerator. Q squared is in the numerator, excuse me. So at this point, we can start building a diagram, interactive animated diagram showing what the prover and the verifier do in the course of the Stark protocol. So we start with the algebraic execution trace. We low degree the algebraic execution trace, thereby obtaining the low degree extended trace. And we compose the low degree extended trace with the error constraints, divide out the zerofiers, and thereby obtain quotients. We turn this huge table of trace and quotients into a Merkle tree by treating every row as a leaf. And then we send the root of this Merkle tree over to the verifier. The verifier responds with an out-of-domain point, which you can think of as an index that's out of bounds into this table. And so that's how I decided to draw this. It points at a row that doesn't live in this table. And so the prover needs to supply that row. And since the error constraints involve transition constraints, the prover needs to supply 2 of them, and the verifier will be able to compute the quotients in that point from those 2 rows of the trace. After sending over those rows, there are a number of deep updates that need to be done. And then the verifier samples random weights used to compute a combination code word. And we Merkleize that combination code word, interact with the verifier, sample a scalar, split and fold logarithmic number of times, obtain indices from Frye, and open every Merkle tree in those indices. Okay, that's the basic workflow of the Stark. And it's going to get more complicated from here on out. Sorry. But the nice thing, though, is that we barely have any superpowers left. The only superpower that we're using here, besides the random oracle model, which is just an idealized hash function, and that's not too strong of an assumption because hash functions exist. The only other superpower is interaction. How sound is this? Yes, question.
Is it correct to say that this summary diagram is a detailed presentation of a commitment scheme?
No, this is a detailed presentation of a Stark. The commitment scheme is embedded in this diagram. You see it twice. That's the triangle, which symbolizes a Merkle tree, and the point in the triangle symbolizes computing the root, and the root is the thing that is being sent from the prover to the verifier. That's the commitment scheme.
Yes, follow-up question. For the hash functions that are not used, we do know how to replace the random oracle model.
Yes, but then you don't get a clean expression in terms of the number of evaluations. And you have to replace that expression q times q minus 1 divided by 2 to the lambda by some unknown insecurity function for finding collisions in the hash function. And then as cryptanalysis on that hash function progresses, you have to update your knowledge of the soundness error. It's a bit of a hassle, and it makes stuff unclean. But yes, you absolutely can make an argument that in the real world, we shouldn't be relying on random oracles, and we don't need properties that hash functions don't have, but random oracles do, at least for this step, right? Because we do think hash functions have collision resistance, we just don't know how much. Whereas for the random oracle, we know exactly how much collision resistance we get. All right. Soundness. Once again, we accumulate all the terms, or we still have all the terms we've accumulated so far. And the soundness of the extra steps is captured by the probability of the malicious prover finding collisions in the hash function. And since we modeled that hash function in the random oracle, we have a very concise expression there: q times q minus 1 over 2. That was the BCS transform. And this is usually where the literature stops, as in, here's a snark, and you can turn it non-interactively with the Fiat-Shamir transform. That's what the papers usually say. They rarely, with a few notable exceptions, they rarely move beyond that. I'm obviously trying to make a complete presentation here, so I will cover it. Fiat-Shamir transform is the last step in our compilation diagram. after applying the Fiat-Shamir transform to an interactive protocol, guess what we have? We have a snark. And since our interactive protocol started from deep Ali, we will end up with a Stark. And back to this diagram, we can identify exactly the stages that are problematic if we want to have a Stark. That's the interaction. How do we replace that interaction with a verifier? Well, firstly, you don't have to. There is a use case for keeping Starks interactive. And it also means if your Stark is interactive, that the total communication cost is less at the expense of interactivity. But so if you want to make it non-interactive, you need to pay. Your total proof size will be larger, but you can do it. But there's another cost. That's not just the proof size, or rather, the proof size is compensating for the more fundamental cost that you're paying, which is you're degrading soundness. So once again, we're stripping away a superpower of the verifier, and the superpower is interactivity. And what the verifier is going to do is going to, or the prover and the verifier are going to do, is they're going to replace every message from the verifier by the result of the hash function when applied to the concatenation of the claim and the transcript up until that point. So at every point, the transcript has grown a little bit, and so the input to this hash function has grown a little bit, and so it's different every time. And so every time the prover gets a uniformly random variable. The intuition why this should work is because the reason why the interactive protocol is sound is because these challenges are hard to predict. And by passing them through a hash function, the challenges are still hard to predict. The verifier can reproduce the same challenges, and now there is a predicate that the verifier can evaluate that determines whether to accept that proof or not. I just showed you a protocol. Soundness, yes. This is the Fiat-Shamir transform. And in order to answer soundness, I'm going to have to do some hand waving. So here's a little digression. How do we prove the Fiat-Shamir security of a interactive protocol consisting of one round? So the verifier sends a commitment. Excuse me, the prover sends a commitment, the verifier sends a challenge, and the prover sends a response. We want to turn that non-interactively. Well, if you study this problem, you might condense it into something like this. Here's a computational task. We need to find an X such that the pair X and the hash of X belongs to a certain set R, a relation R, which is both sparse and uniform. Sparse means that the number of elements relative to the number of pairs is small. And uniform means that the prefix doesn't really matter, or the suffix in this case. So the number of Z for which XZ is in the set is the same as the number of Z for which YZ is in the set. So the prefix X or the prefix Y doesn't really matter if you consider the number of ways to complete the pair such that you get an element of this set. So that's what sparse and uniform mean. And then we can define the task as what is as finding such an X. And then the question is, what's the success probability? We're allowed to model X as a random oracle, but the point is it depends on the number of queries. So if you have a lot of time, you can evaluate the random oracle plenty of times, and you can boost your success probability. So interactive protocols usually have a soundness error that reflects a probability, but when you make it non-interactive, it doesn't really reflect the probability anymore. Is there a question here?
Yeah, so just to be clear, are we defining the relation R precisely as x comma h of x?
No. The definition of the relation R is not given. You just know that it's sparse and uniform, and the task is to find an x such that the pair x and h of x belongs to this relation. Okay. And so if you have only one query to the random oracle, then we know exactly what the probability is, or rather, we don't know exactly. It depends on the sparsity of R, but we can assign that sparsity to a variable called epsilon R. And then if you have Q queries, well, you have Q chances to be lucky. So your success probability grows by a factor Q. And we can apply this to a one-round protocol, where the task is to find a commitment such that the hash of the claim concatenate commitment is in some set of suitable challenges. And from the interactive soundness, we know that this set induces a relation that is sparse. And from uniformity, this is a little hand waving, but by and large, it's safe to assume that the size of this set of suitable challenges doesn't really depend on the concrete commitment given. Now, if these two conditions are met, then we can bound the soundness error in terms of the soundness error of the interactive protocol. We can bound the soundness error of the non-interactive protocol in terms of that of the interactive protocol. And the point is that you have two chances, you have Q chances to sample a suitable challenge. And so your soundness error grows by a factor of Q. And so if your interactive soundness error is 2 to the minus 128, and you want to consider adversaries that have time to compute 2 to the 64 hash function evaluations, then your non-interactive soundness error is only 2 to the minus 64. Right. If you want to lift that principle to multi-round protocols, it's difficult. Because yes, you can find a relation defined in terms of the interactive protocol. You will be able to determine that that relation is sparse, but it's very difficult to find a compelling definition of uniformity because prefixes in the transcript matter. You can have good starts or you can have bad starts. And so there's no such thing as prefix independence. And so uniformity, maybe you might be able to save it, but it's not clear how. So instead, what we consider is round by round soundness. And the idea here is that we take a set of all transcript prefixes, and we partition this set into doomed prefixes and not doomed prefixes. And so this induces a finite state diagram, or an automaton, if you will, where in every iteration you consume one message from the transcript and you move around according to one of the arrows. If you've consumed the last message from your transcript and you're in the doomed state, then you must reject. And if you've consumed the last message from your transcript and you're in the not doomed state, you must accept. And so you're going to fit the interactive protocol to this diagram. and you're going to analyze the probability of traversing the arrow from the doomed to the not doomed state. And this is a razor thin focus of the relevant question, because it's actually not too difficult to answer this in most cases. I'm not going to answer it, though. I'm going to refer you to the papers. The round-by-round soundness of a protocol implies Fiat-Shamir soundness. It's not too difficult to build an intuition of that. The round-by-round soundness of Frye was established not too long ago. It does use very arcane coding theoretical results. The round-by-round soundness of Deep Ali, I don't think was ever established, but then a specific example of Deep Ali in the form of ETH Stark did prove its round-by-round soundness. All right, that was the Fiat-Shamir transform. That pretty much concludes the presentation that I intended to finish yesterday. Yes, question?
It was capital S. We're talking about the unwavering.
Yes, that's the set of suitable challenges, which obviously depends on the commitment, but since we're assuming uniformity, the only thing that matters is the size. And then the size is basically the same.
What are we assuming?
Of the relation induced by the proof system. All right. So then the last thing I wanted to cover in this presentation was topics that I will cover in the next, but unfortunately I won't be able to cover all of these topics. So I'll need to make a selection. Let's have a look at the time. Lunch starts in half an hour, right? So I have half an hour now, and I have 20 minutes? 40 minutes. I have 40 minutes now, and Sophia has also granted me half an hour from her time slot. So I think I really want to cover zero knowledge, and you know what? Let's just plow ahead with quotient segments in the next presentation. And then I think at some point in the optimizations section, the time will be to end this presentation. And then after Sophia's lecture, I'll cover zero knowledge. So, escape. Advanced CK Starks, Control L. Here we go. For this presentation, as for the previous, the slides are available on my website, asc.ink. And the techniques in here are slightly more advanced. Since I already had a retrospective at the start of this lecture, I think I will run through this retrospective in short order. But the point is that we will be returning to this diagram again and again and adding on features and components. Okay. Firstly, batching. I already covered batching. The particular variant of batching that I covered was linear batching, where you would sample a uniform scalar for every vector that you sum into the batch. But the downside is that you need to have as many uniformly random scalars as terms in your batch. And so people also like to batch using only one random scalar, and then the concrete weights are derived from the powers of this scalar. That corresponds to a univariate polynomial evaluation. And then there's another form of batching that's less popular, but just as possible,
where you sample logarithmically many random scalars and then take their Kronecker product to obtain a linear number of weights. And so you have this trade-off range of options between where you trade off the amount of randomness required against the soundness error, which is the greatest for univariate and the smallest for linear. And multilinear is in the middle, both in terms of required randomness and soundness error. Right. And so if we're going to use univariate batching, then this very long vector R of random weights here turns into a single scalar with the context that we're going to take powers of this single scalar. All right. It's nice also, hang on. Not sure what the difference is here. Yes, so it's nice to move as much of the batching as far ahead in the protocol as possible. And so we can start batching the big matrix ahead of time. And that's what happens here. So we sample this R soon. We sample this R, we do part of the batching, then we do the deep update. And we need to do 3 updates, so that gives us 3 vectors, and then we complete the batching on those 3 vectors. And so we move the univariate batching. It's not quite univariate because you do need different weights here, but it's mostly univariate. We move that ahead 1 step in the protocol. And why stop there? You can even move a large part of the batching earlier in the protocol. Now, the difference is this was one huge matrix, low degree extended trace and quotients. And now we're going to commit to the low degree extended trace separately in order to sample weights, which are used for batching air constraints and therefore quotients. And that means that we can compress this huge quotient table into a much smaller table, 1 vector, but there's a good reason why it's represented here as a rectangle. So this is just another instantiation of moving the batching as far ahead as possible. And the trade-off is, yes, you have 1 extra Merkle tree, but in exchange, you get a much smaller quotient table. Great. So why did I represent that quotient table as a rectangle? Well, it's because there's this huge monster that I swept under the rug and need to answer now. All of the previous is perfectly valid if the degree of the error is 2. And there are, in fact, some ZKVMs out there that use error degree 2, and so all of the previous is valid for them. But we actually use error degree 4. And so what do? Firstly, what's the problem if your error degree is greater than 2? So you compose your trace polynomials with the error polynomials, and if the error degree is greater than 2, then you obtain univariate polynomials of degree greater than 2m. You might be able to reduce that by a term n when you divide out the quotients, but the point is that you end up with polynomials that are larger in degree than the trace polynomials. And so if you extend those polynomials into code words of the same rate, you have code words that are longer. And they certainly don't fit in the same table. And maybe you don't want to waste time computing NTTs on vectors of this length. So, yes, you can batch them, but it would be nice to have vectors of the same length. What do? We split. Same old, even, odd split, except if you need to split it into k components. For k is different from 2, you can use a k-wise generalization of the even mod split. And so that's what the rectangle previously denoted. Now, if we do the out-of-domain point evaluation, we get a row for the trace, but we need to get a row in a different point for the quotient segments, so that the error evaluated in the out-of-domain row of the trace gives the quotients in this point. So this is what the updated diagram looks like. We have a rectangle here, and the out-of-domain point gives us a pair of out-of-domain rows in the trace, and in some other well-defined point as a function of z, an out-of-domain row of the quotient. All right, I think grinding is the last thing I'll cover before we go to lunch. And then zero knowledge will be the topic after Sophia's talk. So grinding is a nice little trick that allows you to reduce the soundness error in exchange for a small prover cost. And therefore, since you're reducing the soundness error, you can compensate, or rather, you can use this to compensate for sampling fewer indices in Frey, which leads to a smaller proof. I mentioned one that can be verified faster. So we have this interactive protocol, and in the second to last message, and possibly even messages before that, we're going to require proof of work from the prover. So the prover needs to sample a nonce that satisfies a proof of work equation. So you can imagine that the images of this hash function are identifiable with some integer, with some fraction between 0 and 1, and then that zeta symbol captures how much work does the prover need to do in order to sample a suitable nonce that satisfies this. That's grinding, that's it. Now, if you look at the soundness error for the interactive protocol, that's epsilon. For the protocol with grinding, there's two events now. One is the verifier accepts, and the other one is the proof of work is satisfied. And if the malicious prover runs through this protocol in a straight line fashion, probability that it is satisfied really is zeta by definition. And so if you look at the amount of work that the prover has to do for the interactive, for the original protocol, that work is W. But if you add a little bit of grinding, then he also has to solve the proof of work puzzle. And that requires zeta inverse hashes on average before, or in expectation, before you find a suitable nonce. Why is this a good trade-off? Well, it's obvious once you start putting numbers, right? So let's select zeta is 2 to the minus 1024. So in expectation, the prover needs to do 1000 hashes before he finds a suitable nonce. So the workload for a reasonably large proof is an order of magnitude larger than that 2 to the 10. So the workload, it's not uncommon for the workload to be 2 to the 30 finite field operations or hashes. And so doing 2 to the 10 extra hashes is next to nothing. But in exchange, we do get 10 bits of security in our soundness error. That's 10 bits of security in exchange for 0.1% extra time spent proving. That's a great trade-off, but it doesn't scale. right? Because as soon as zeta becomes too small, then the proportion of time spent solving the proof of work puzzle starts weighing and outweighing this original work factor. All right, that was grinding.
Sorry,
Here's a question, yes.
could you repeat how that grinding reduces the soundness error?
Because now you need to verify the original verification predicate and something else. These are two independent events.
Yes, but like intuitively, you don't need any kind of knowledge to generate that nonce.
I'm not talking about proof of knowledge. I'm not talking about knowledge soundness. I'm just talking about soundness.
Okay, all right.
That's a reasonable open research question. Does grinding extend to proof of knowledge? I don't know. All right, I think I will pause my presentation at this point, and then resume in the afternoon. Thank you.